Very good evening to the esteemed attendees to this prestigious uh, lecture on the occasion of the National Technology Day by INAE. I am joined by none other than Dr. Anil Kakodkar, who is an extreme authority on the subject of nuclear science. And we have with us Mr. J.D. Patil, President INAE. It is my distinct pleasure, firstly, to welcome Mr. J.D. Patil, President INAE. With that, I will hand over the process to Mr. Patil, sir, President INAE, to welcome our esteemed speaker today. And with that, Mr. Patil, sir, over to you.
Thank you, Shobhit Rai. For me, Dr. Kakodkar has been one of those icons one looked up and grew with. He hardly needs any introduction for what all he has done for India, and for decades together, what Dr. Kakodkar's contributions to the sector has been. This year, as we know, the PFBR just got commissioned, and we thought with the energy bill, rather the nuclear bill, which the parliament approved, on backdrop of these very two major opportunities, which the government is taking the futuristic steps, we thought which better person we can find than Dr. Kakodkar to speak, an authority in the subject itself. And that's where, as INE, we decided to put in a request, and this is where we are today meeting. We would be hearing Dr. Kakodkar on the thorium specific subject on how is India's outlook and way ahead. Dr. Kakodkar doesn't need any introduction, but to just say just few words about his key contributions in the India's advancement on nuclear energy, and as PHWR, and as well as the advancement of thorium utilization for India's energy independence, and pioneered the design of the advanced heavy water reactor, which we know will power the whole country for I don't know how many hundreds or thousand years, which we'll learn from Dr. Kakodkar. Strategic sovereignty to India, which we know we again are not signatories to any of the treaties, but we are recognized as a nuclear country. And this was one of those big contributions Dr. Kakodkar made as a key figure in India's nuclear tests in 74 as well as in 98. I remember those days as a young man in still studying at IIT. We used to go to IIT, the BARC campus, and my aunt used to live very close to where Dr. Kakodkar used to live. So we used to look up to Dr. Kakodkar, as I said, in an awe during those early days. The entire nuclear power pack and the various stages of the nuclear power development, as well as the nuclear powered submarine related developments of the light water reactors that the submarines use. He played a very crucial role on that. And subsequently, with the 123 agreement having been signed with the US President and the Indian Prime Minister, he played an enormous role in the agreement as well as the civil nuclear cooperation with the international community, which became the hallmark of what began in India as a commercially funded reactors that started coming into India. The international nuclear diplomacy as a result grew, and he played a crucial role in negotiations with the US, as I said, and the nuclear suppliers group to secure Indo-US nuclear deal, allowing India to join the global nuclear mainstream, as I just said, without being signatory to the NPT. Rehabilitation of our existing reactors was yet another major challenge. We are a country which never ever had any major nuclear, I would say, incident, and good that our scientists, the likes of Dr. Kakodkar, whom he incubated in those early age of theirs, obviously did a lot well, and the successful rehabilitation that happened at Madras Atomic Power Station in terms of the cooling channel replacements were all kind of conceptualized and being continued in the form of continued operation without being written off and closed down. Institutional and educational development he's been contributing in the form of establishment of the Homi Bhabha National Institute, which we know has been playing enormous role along with the National Institute of Science Education and Research, NISER, and the DAE Mumbai University Center of Basic Sciences. He's been chairman to the Board of Governors of IIT Bombay. I was privileged during that period to be recognized at his hands as a distinguished alumni of IIT Bombay, and that was one of that cherishing moment of receiving that kind of recognition at the hands of Dr. Kakodkar. He's been a member in multiple advisory committees and has chaired multiple high-level committees on railway safety, rejuvenating the national technical education in India, and the like. The technological vision, he led the development of Technology Vision 2035 for India and has advocated for development of the Chillage, the city in a village kind of a model with sustainable rural development powered by advanced technology. For his stellar service to the nation over decades, he's been celebrated and awarded with Padma Shri in 1998, Padma Bhushan in 1999, and Padma Vibhushan in 2009. Among the most celebrated scientist engineer of our fraternity, been a president of INAE in the earlier years, and today I am privileged to be in that chair. And sometimes one wonders whether you are really going to be measuring up to the kind of positions has been occupied by those tall heroes the nation really doesn't know too much about in the form of being the unsung ones. So, with that introduction, I won't speak much about Dr. Kakodkar, but request Dr. Kakodkar to take over. Sir, we need your guidance on a continuous basis. We still look up to you in terms of guiding us to how to enter into the small, medium, or the SMRs, as we keep talking about, in terms of how we need to go ahead. What I need, in your view, the institute that you built in the earlier years, institution that you built, need to do towards some of those initiatives and take it forward from there. So all to you. I just hand over to you.
Thank you, Mr. President. You have been very generous, and I only hope I will measure up to the expectations that you have raised so high in the few sentences that you said. I would also like to thank INAE as a whole for this opportunity to be a part of the National Technology Day program, the lecture. And I have deliberately chosen the aspect of energy independence through nuclear energy, or more particularly through thorium. And of course, it is of current interest because, as you said, we have achieved the first criticality of PFBR recently, and that has brought the country into the second stage of India's nuclear power program, which has a tremendous role to play, both in energy security, but as I would like to call it, more in terms of the energy security of the country. I would also like to use this occasion to clarify a few things. I must clarify that whatever I'm going to speak, I'm going to speak as Anil Kakodkar as a person. And please don't attach this with any official policy or statements. But I am going to talk about what I think India should be doing in terms of securing its energy independence. So let me share my slide deck. So the point I like to first highlight is, see, right now we are in the midst of a serious threat to our energy security because of the blockade in the Strait of Hormuz. And compared to total energy requirements or total oil requirements of India, maybe 20-25% comes from there. But the kind of hit the country would have to take, we can all sense, because it's a part of the common discussion today as to how the country has to brace with this major challenge. Simultaneously, we have this target of making India net zero in terms of its energy use, net zero compliant. And that also would mean over a period of time to move to clean energy sources. And now that's a big challenge, although we have time. The target for that is 2070. But I think it is a very tough target, and I'm not too sure whether we can go away from fossil energy anytime soon. But anyway, that is not the subject of today. But the same fact has kind of made the challenge of clean energy transition, and more particularly and energy independence, much more daunting. As it is, we have been facing challenge of meeting national requirements. We have been very good in terms of developing technologies, in terms of scaling up to the level of expectation. And now that expectation has gone up many folds, or for that matter, an order of magnitude more. So we have a big challenge. So, and it is in that context that I want to make some propositions. But as I said earlier, please take them as my own propositions as an individual. Now, I have deliberately put some figures at the top of this slide, and they all are kind of, except the one Kudankulam picture in the center of this figure, all other technologies, they're all big plants. They're not small toys. They're all massive plants involving huge investments and efforts by many, many people. But these are all indigenous efforts. And I'm sure what I'm saying will be also applicable to PFBR, which has just gone criticals. So it is too early to make a statement about its final performance. But all of them have worked to what you will say global standards in terms of the performance, capacity factor, and also in terms of the cost, the economics, for electricity production, the tariff of electricity produced. And but there is this next challenge which I mentioned. We have to learn to be able to scale up. And that is where I think not just the engineers and scientists within the Department of Atomic Energy, but engineers and scientists in the country have to come together and lead the path. And of course, INAE being the cream of engineers of the country, INAE must play a very important role in this matter. How do I change the slide? Yeah, okay. Now, I want to begin with a small tutorial stating the obvious for many of you, but for some of you who may not be from the nuclear domain, I think some basic things, stating them for clarity may be important. So the first point is nuclear energy, or more particularly nuclear fission. For that to happen, we require materials which are fissile, which can fission and produce nuclear energy. And the only naturally occurring material is uranium-235, which is a very small fraction. The isotope uranium-235 is only 0.7% of the natural uranium that exists in the nature. The rest is the other larger isotope, uranium-238, which we call fertile. You can't fission it so easily, but it can be converted to a fissile material. For example, uranium-238, when it absorbs neutron, it can become plutonium-239, which is as much a fissile material as uranium-235. Another important nuclear material is thorium. There is only one isotope of thorium, thorium-232, and all of it is fertile. It doesn't have any fissile content. Importance of thorium to India is that we have world's largest resource of thorium. The second aspect, as you could make out from what I said earlier, is in a reactor, while you kind of release energy and produce electricity through the fission process, but you also produce fuel by converting fertile materials to fissile material. And there is a category of reactor, the fast breeder reactor, which in fact produce more fissile material than the fissile material that the reactor consumes for production of electricity. So a nuclear reactor is both an energy factory as well as a fuel factory. And that's an important thing that we must recognize in case of nuclear energy. Now, the fact that we don't have too much of fissile endowment, of course, recently the explorations that have taken place have identified significant uranium resources, but then the ore grade is very poor. And so cost of uranium production compared to the international price of uranium is very high. And so most of the current program seems to be based on imported uranium, and which actually is a matter of worry for me. And that's why I'm going to advocate this question of thorium. But I'll come back to that. But this is that we have plenty of thorium and only modest quantities of uranium is the basis of our three-stage program. And these three stages are linked. They cannot be seen in isolation because they are linked through what are known as fuel recycle facilities. You irradiate uranium in first stage reactor, some of the uranium-238 gets converted to plutonium, But then you have to recycle, you have to separate plutonium and recycle it in a fast breeder or the second stage reactor along with uranium. And similarly, the second stage reactors, whatever spent fuel comes out, we have to recycle both in second stage itself because we have to use the bred material, but also when you irradiate thorium, you should be able to take it to the third stage. So there is this connection between them. And in the context of energy security, or for that matter, safety, we should also recognize that the energy density of nuclear materials, uranium 235, plutonium, uranium 233, is around 300 or 3 million times higher than coal. So we are talking about very high energy dense technology. Now, with that basics, let's look at the, the India's energy challenge. So I would like to first fix how much energy we would require in equilibrium. Not today, but when India becomes fully developed, what kind of energy demand we will have and whether we will be able to access that kind of energy when such a demand arises. And for that, this correlation which is there on the figure is very useful. I'm sure many of you have seen this several times. The blue triangles on top of this correlation, these are the advanced countries. So if we want to be a Viksit Bharat, we want to be an advanced country like these countries, then we should be able to get access to energy, at least to the extent of the minimum required to be there. And that is represented by this dotted vertical bar. And so we should get uh, energy access somewhere up to this point, corresponds to 0.95 Human Development Index. It corresponds to per capita energy consumption of the order of 2,400 kilogram oil equivalent per year per capita. And now that multiplied by the population would tell you how much energy will require every year to be Vikasit Bharat. We can also take into account the fact that as the technology moves, as electrification moves, the efficiency, energy use efficiency goes up. So you can discount, and I would imagine that you can discount to the extent of 40%, in the sense compared to what will you require 40% less because of the improvement in the efficiency and all. But even after accounting that, you would end up with a number something like 28,000 terawatt hours per year. So this is my target. Viksit Bharat, we should. There are many people who say why India should have so much energy. Many people say why you want 0.95. You put 0.9, the requirement will come down drastically. When you put 0.85, it will come even more. But I think we are living in a competitive world, and we know the value each country attaches to other and what it takes for other countries to respect us. And so unless we are able to match everybody in that Viksit country category, I think the life will be difficult in a competitive environment. And so for me, the target is 28,000 terawatt hours per year. Now, keeping the clean energy scenario in view, the net zero target, all this has to come in the form of clean energy or energy forms which does not emit too much of carbon dioxide. Of course, the thing that immediately comes to your mind is renewable energy. Now, in my assessment, these numbers are hard to get, but you can survey this. In my assessment, the upper bound total renewable energy potential in India is around 8,000 terawatt hours per year. And that leaves a big gap of 20,000 terawatt hours per year. And that can be bridged only by nuclear, because large hydro is, in fact, I have included that as a part of renewable energy, although in normal statistics, you keep large hydro separate, but here that 8,000 includes large hydro as well. So we have double challenge. We have to, from the current consumption level of around 10,000 terawatt hours, we have to take our consumption level to 28,000 terawatt hours. And in that, we have to grow nuclear generation equivalent to something like 2,500 gigawatts, which is equivalent to 20,000 terawatt hours. And I myself, I'm doubtful whether such an ambition can be met. So whatever one does not meet, the only answer would be to depend on fossil fuel, and to make sure that we don't emit carbon dioxide, we have to talk about fossil energy coupled with the carbon capture, utilization, and sequestration, which of course is possible now, but there is going to be huge cost associated with this. So that's broadly the challenge of how do we go to 2,500 gigawatt electric capacity. As I said, this is since I was involved in building Dhruva, that is the pole star for me. We have to move in that, and probably will never be able to reach there. So let's now look at the components. In the table that you have on the left-hand side of this figure, you have different clean energy forms, and what is the contribution they can make in terms of their potential. And you notice that I won't now talk about things other than nuclear, but you notice that nuclear energy used in open cycle form, and I'm assuming that we get access to as much as 10% of the world's uranium, world's commercial uranium, but that will allow us to access around 400 terawatt hours per year, and at that rates, maybe for 50 years. Now this itself is large number, but it is very small compared to India's energy requirements. And so I think today what is happening is we are kind of growing our program because we are able to get uranium from outside. That's a good thing to start. But we can't be dependent on that for all time to come, because even 100 gigawatt program that we have, say, India's nuclear energy mission, that will create significant access challenge in terms of getting uranium from global market, because when your share in the global market becomes large, you have to be really powerful to be able to acquire that. Otherwise, you know what global politics does, and we are actually going through that experience. Another point that we need to take note of is on the demand side. Earlier, we required energy in the form of electricity, heat, process needs, agriculture needs in our kitchens, so on and so forth. Now, primary energy in those days, or even today, used to be in the form of fossil energy. So the energy you get first, see that in the form of heat, mostly. Some of it can come in electricity and other forms. And then that heat you convert to other forms, depending on the demand. by different segments. Now I think things are likely to change because all renewable energy except biomass, it would primarily produce electricity. Nuclear also, it would primarily produce electricity. Of course, solar, thermal, and nuclear can also deliver high temperature heat, which can be used for industry and other purposes. So the transformation, energy transformation, quite apart from the transformation at the supply end, even the supply demand transformation is going to see a big change. Earlier it was heat to electricity, most of it. Now it's going to be electricity to whatever else, most of it. And of course, it all depends on how we give shape, because electricity is a much higher quality energy, and it will be too much if we convert electricity to heat. We should always take the energy from a form to a higher level form. The second aspect is demand segments like kitchens. They require clean fuel, while electricity can also be used for kitchens. But Indian cuisine, you require flame for cooking. And to be able to get clean gas in the kind of a clean energy environment, except biogas and CNG or PNG that you get. Uh, if you say that PNG we don't want to use because it is fossil energy, and the biogas we don't focus properly because there are so many claimants and demand on biogas, then we'll be forced with a choice of taking hydrogen to our kitchens. And I would say that maybe that's a thing that may be possible in future, but it will be too risky to take hydrogen in our kitchens right away. So that's an important point I thought I would make. Now, with that background, this is where the current nuclear power program is. Around 8,800 megawatts operating capacity. So notice that in our original three-stage program, of course, Bhabha's time, the first stage was even smaller, but after the review that took place in Dr. Ramanna's time, the first stage we said we can go up to 10,000 megawatts. Now we are very close to that. We'll cross that maybe in an year or so. We're very close to completing whatever we had decided for the first stage program. Now the spent fuel, which was to go to second stage, is all accumulating, is ready to be delivered. But we are not quite there, although PABR, we have gone through criticality, but I think growth of second stage, it has to happen quite fast and quite soon. And I see there is some time gap there. I'll come back to this issue because this is the main theme that I want to talk about. And then, of course, there is around 7,500 megawatt capacity under construction, more in the planning. So you expect around 22 gigawatts fully tied up, and that capacity will be realized as soon as the projects which have been already launched get realized. We're also these two sites at Jaitapur and Koada, where we expect the EDF and the Westinghouse reactors. We've been waiting for now decades. Nothing is really happening, but those sites are available, and because sites is a very premium thing. But and I'll talk about this a little later. We have now this mission to reach 100 gigawatt, 100,000 megawatts by 2047, and we have the net zero target. The country wants to become net zero compliant by 2070. So it is in that context that I think transition from uranium. Today, all focus is to do nuclear energy based on uranium. Now, that, of course, we must grow. We can't slow down the program. But we must make efforts to make sure that we transition from uranium to thorium as fast as we can, because by the time we advance into this 100 gigawatt program, I feel pretty certain that we will start seeing the uranium access constraints from international market, and that would be about time when we should be able to start leveraging thorium for large scale energy production. And that time scale is not very, very large. In fact, there was a time when our program was almost coming to kind of not halt, but tending to that. The capacity factors was going down, and we worked for opening up the civil nuclear cooperation, got access to uranium. The intention behind that, behind opening of international civil nuclear cooperation, was to remove the hurdles in accessing uranium, because we couldn't get any uranium at that time. Now we are able to get access to uranium, but that does not mean that the priority for thorium should be diluted in any way, because that was never to be compromised. And I remember in that discussion, Dr. Kalam, who was, of course, I was quite close to him, and he was president at that time, president of the country. He was concerned whether by getting this uranium, the thorium, people will dilute thorium priority. And I actually kind of assured him that, look, once we get access to more uranium, we can actually speed up the thorium ambition. We can accelerate thorium. And I explained to him, which I'm going to explain to you here. But at this moment, the trend which I see is quite disturbing, and people are merely going ahead with expanding capacity with imported uranium. So that is a matter of concern. Growth, I'm happy about, but getting into vulnerability domain is something that we need to deal with. Now, the number of new developments, for us to be able to make use of thorium in a big way, we need to do a number of further developments beyond PFBR. And that is PFBR. Of course, we have to take PFBR to full power. We will have a few follow-on fast breeder reactors, very similar to PFBR. But beyond that, we would also, it will be necessary for us to, to support growth of thorium on a large scale. You want to create a large thorium irradiation platform. Now, that would require a set of nuclear reactor and as well as nuclear fuel cycle technologies based on mixed oxide fuel, the way PFBR is, but also based on metallic fuel, and then followed by based on thorium fuel, the thorium reactors and the fuel. So you have to develop the reactor technologies for these purposes, as well as the fuel cycle technologies for these purposes. So I think we need to recognize that while PFBR, I am also very euphoric about this, and it's certainly a cause for celebration. But we have to recognize that for thorium to be used on a large scale, there are several steps yet to be covered. And to my assessment, that is around 3 to 4 decades away. Whereas, as I mentioned earlier, the uranium constraint you would start seeing much earlier. Now, on the other hand, a substantive PHWR capacity is coming into existence between now and 2047. That is, within next 20 years, you will have 100 gigawatt uranium-based reactor, and kind of apart from electricity supply, they also constitute a sizable capacity for irradiation of uranium-233, particularly because out of this 100 gigawatt, I'm sure nearly half of it or little more would be PHWR, which I put it to you, which is ideally suited for thorium irradiation. Actually, PHWR is a very flexible in terms of the fuel cycle, so it can be also used for irradiation of thorium. And that's an opportunity that I would want to leverage, and we should move the country in that direction. Now, just to understand which way to go about. Of course, we know how much uranium and thorium we have in India. We also know how much uranium and thorium exists all over the world. Of course, when we talk about the world, we talk about uh, kind of commercially viable grades. When we talk about India, our commercial viable grades are maybe much leaner compared to what is considered commercially viable elsewhere. But leave that as it may. I think it is important that uh, we start making efforts to irradiate thorium in PHWR. Now, obviously, thorium absorbs 3 times more neutrons compared to uranium, so it's going to be a load on the reactor. And conventional wisdom will say you put thorium in PHWR, it's going to need more uranium to support that load, which is actually true, or which was actually true when the fuel technology did not allow burn up beyond, say, 25-30 gigawatts. Now that fuel technology is gone to a level where you can get even up to 60,000 megawatt days per ton burn up in water systems. I'm not talking about fast reactors, you get much higher burn up, but in water systems, there you can get a lot of advantage of the energy that would be generated out of in situ produced uranium-233. So can we think of a fuel which will maximize production of uranium-233, which will give enough reactivity to the core in spite of the fact that you have to address the load caused by thorium, and keep the uranium-238 to a minimum, because that is what will go to plutonium. And plutonium, of course, is an excellent fissile material, but it burns very fast. So it does not allow you to give or derive as much advantage from thorium as uranium-233 would. And so I think if we can, now in civilian domain, one can use enrichment in uranium only up to 20%, which is called HALU. 5% to 20% enrichment is called HALU. So what if we take the permissible uranium, permissible in the civil domain, HALU, and then mix it with thorium, as large a thorium as the physics will allow, and look at how much burn up we can get. And it so turns out that you can run the reactor with up to even 60,000 megawatt days per ton. You can run the reactor without making any change. And well, this is an issue which is some people are debating, but I am convinced, because I have seen detailed calculations done somewhere else. And so you can use the same reactor in 200 megawatt, make a very minimal insignificant change. In 700 megawatt, no change at all, and get large burn up. Immediate advantage is the spent fuel quantity shrinks. And that's a very large advantage, because when you have to handle the back end of the fuel cycle, back end of the PHWR, the quantity of spent fuel that you need to handle will decide the costs. And with as compared to 7,000 megawatt days per ton burn up that you will get with natural uranium, if you go to 7 or 8 times more burn up, then the spent fuel quantity will shrink by that much. When there is a huge cost saving there. There are also savings in safety and all. I'll mention that in the next slide, but uh, uh, this is something I know is proven, and I'm sure that debate will be solved completely. But if you do that, then the spent fuel arising out of such a configuration would contain in the uranium vector sufficient enrichment, not so much in the form of uranium 235, but more in the form of uranium 233. Of course, there will be some other uranium isotopes, but you can just separate the uranium and thorium in a pyrochemical process, which one will have to anyway adopt when we go to third stage, following the metallic fueled fast reactor to third stage. It will be inevitably that technology, which is a part of our agenda. So we advance that development, we advance the thorium reactor development, and then this uranium vector can be straight away used as fuel. Of course, it will be more like a molten fuel in a molten salt reactor, in my view. But whatever that detail is a separate thing. But it can be used as a fuel. So, in theory, the, the schematic on the bottom left-hand side, which is the three-stage strategy. By the way, this remains because fast reactors will remain. We have to keep breeding more fissile material. India's energy requirements are going to be perpetual. So till fusion arrives on scene, we have to worry about fuel production. So that remains. But we can, before the fuel supply vulnerability hits us, if we adopt a scheme which is there on the right hand side bottom, then you get that fuel and straight away put it in a thorium reactor, and you can add capacities now which will be fueled by thorium, because in such a reactor, if it's a breeder, thorium breeder, then you convert to 233 and you consume it in city, and from externally you keep feeding thorium, and that I think is an eminently possibility, and I'm saying this with some experience, some insights which I derived out of working on advanced heavy water reactor, and also interacting with some other groups knowledgeable in this area. So this is what has been done. There is a startup. It's a US startup because I couldn't find anybody in India take interest in this in spite of a lot of persuasion. So they have made these pellets out of HALEU thorium. These are hollow pellets because you require space for holding fission gases. You also need a stronger cladding when you talk about such high burnup, and some such minor changes, but the external configuration of the fuel bundle remains exactly as it has been all along. And as I said earlier, on the reactor side, there is practically no change. And this was, the pellets were made by a university in US, Texas A&M. The irradiation was done at Advanced Test Reactor at Idaho Falls, which is one of the Department of Energy's national lab. And what you are seeing in this picture are the neutron radiographs of the spent fuel, which has come out of this irradiation. And this, of course, is at around, I think, 20 or 40,000 megawatt days per ton. But they have actually completed the campaign and realized full 60,000 megawatt days per ton irradiation. Now, I told you there are other advantages, and I listed some of them here on the left-hand side. and that is, with thorium, because it produces uranium 233. There is also some poison added, which also depletes to balance, so that this reactivity depletion is very gradual, and that's what enables higher burnup. And because of that, the reprocessing burden is much lower, as I told you. Important thing is, this gives an opportunity for India to go global. India can market these technologies. India can, the growth of nuclear power, particularly in emerging economic countries, is not at the rate at which it's required, because that is where the energy demand is the fastest or highest. It's not higher because of the concern of proliferation. And, we know that world at large, except exceptions like India, France, Russia, all countries in the West, they have more or less given up on closed fuel cycle, nuclear fuel recycle. And, uh, and that's for fear of proliferation. Now, with this fuel cycle, this is proliferation resistant. So I think it can create a significant demand for this kind of technology globally, and India can be a supplier of that kind of a technology. This fuel is much more accident tolerant, because melting point of thorium is higher than uranium. Conductivity of thorium is also higher than uranium. So the temperature difference between the melting point and the operating temperature in case of thorium fuel is significantly higher, and that gives you that risk. And we can also add some additional accident tolerant features. So I think this the HALEU thorium fuel in PHWR has its own economic case, regardless of our Indian interest in use of thorium in the long run. It actually will produce unit energy cost, which is cheaper compared to unit energy cost produced using natural uranium. So I have come towards the end of the. So it is on arguments of this kind that I think we should emphasize on use of kind of hasten the use of thorium or thorium utilization. And for me, a clear-cut way is the use of thorium HALEU fuel in place of natural uranium in PHWRs. This would enable thorium irradiation at scale, just like one would want to do of thorium irradiation at scale in FBRs at a point whenever it becomes feasible. And while at the same time you derive several advantages, which I already mentioned, and this means that there is an economic case for use of HALEU thorium in PHWR as it is, and all the other is the further advantage, particularly for the Indian program. So this should enable significant electricity generation capacity sustainably fueled by thorium. And rough estimate to me, now these are all, I only do back of envelope calculations. So, but I know what I'm talking about. So the rough estimate would suggest that a PHWR running on thorium HALEU fuel could support a significant new capacity of the thorium molten salt reactor on an annual basis. Annually, you can add a significant new capacity once you have PHWR running on this fuel. And I think this is doable. We can start irradiating this fuel in PHWR now. And I think as soon as the reprocessing technology for the fuel, which is anyway part of our 3-stage program, as I said, as well as the molten salt reactor technology, which also is required for the 3rd stage. And I would say we should realize that in, say, around coming next 10 to 15 years. And from that time onwards, one can start getting energy out of thorium as against maybe more than 30 years, which would be the otherwise. So that is the thesis that I would want to propagate, essentially to make sure that India realizes its energy independence, because thorium is so large that we can meet all our energy from Indian landmass and not dependent on any import or suffer vulnerabilities of that kind. Now, availability of thorium HALEU fuel recycle technology for feeding TMSRs and development of thorium molten salt reactor, which I already said, would need to be ensured in about 10 to 15 years from now to start producing electricity from thorium. These technologies are anyway part of technology development agenda for the 3-stage nuclear power program. And so, to come back to the closing slide or closing statement, energy security, to my mind, is about eliminating vulnerabilities in meeting our energy needs. Realizing energy independence should be our end objective. Now, many times the question is asked, why are we not doing this all ourselves? Now, the question is, proving such a burn-up, something which has happened in a short time, is not possible. We don't have such irradiation facilities in India to prove that. So I think we need collaboration, and we have collaboration agreements in nuclear domain with several countries. Now, I don't see those collaboration agreements as a pure vendor-buyer relationship. In the sense, say that I have a collaboration agreement under which somebody will set up a reactor here and I'll pay money through my nose. According to me, is no collaboration. That's a business deal. If it's a collaboration, I think it should be joint partnership as equals, develop it together, and create a win-win situation, benefits on both sides. And if you do that, you can actually achieve. In any case, today natural uranium we're importing, so we can as well import HALEU. We can as well collaborate with countries to carry out irradiation, which anyway has happened, so we've gone past that. So this notion of self-reliance, I think we need to be clear in our mind, and we are not weak today. We have faced much tougher challenges when the civil nuclear cooperation was being designed. So I think now everything we have to build on that, and the next steps are not at all difficult according to me. And so we should move towards collaboration, which are win-win situation for participating parties. And I somehow, as I said earlier, I want to repeat, building vendor-buyer relationship is no collaboration for me. That can be done even as a business deal. In nuclear area, it becomes important because there is sensitivity, but you don't call it collaboration. So that's the simple message that I want to present to the fellowship of INAE. And I think it is important for energy independence of the country. So that's my Technology Day message to the fellowship of INAE. Thank you very much.
Thank you, sir. Thank you very much.